All right, section 7, we're going to look at a different type of function, which is called a piecewise function. A piecewise function, we're going to have lots of little parts and lots of little terminology we have to define. But in general, a piecewise function is going to be some function that is defined by different functions for each part of the domain. So let's go ahead and write one and see what it looks like. So what it'll generally look like is we will have some function that's called f of x, and then we will have these different pieces. So maybe I'll have 2x plus 1, I'll have a line piece, and then maybe I'll have just a 5, just a constant piece. And then maybe I'll have x squared minus 4, a quadratic piece. So you have these three pieces, a line, a constant, and a quadratic. Now, you don't know which piece you're using unless you define the parts of the domain. So typically, these are our different functions. And then next to it, we're going to put some pieces of the domain. So maybe I'll put x less than 5, x equal to 5, and then maybe x greater than 5. So what you see is you have these different pieces of the domain. So this part of the function is good for x is less than 5. This part of the function is good if x is only equal to 5. And this part is good if x's are greater than 5. And it doesn't have to just be that. It could be anything you want. I could have a different one. Maybe I just have two pieces. Maybe I say x squared minus x plus 1 when x is less than 1. And maybe I say it's x plus 1 when x is between 1 and 0. So in this case, there's really nothing beyond 0. It's defined for x is smaller than 1, and then between 1 and between 0 and 1, essentially. And, well, let's go 2, because 2 would be bigger. Between 1 and 2, something like that. So you could have this kind of function, right? So these are piecewise functions. And so we have these different pieces that are defined for different x's. So the way we evaluate a piecewise function, we're going to substitute our x values into the appropriate piece. Okay? So for example, let's go ahead and take our purple example here. Let's go ahead and take this example up here. And let's say I wanted to figure out what is, I don't know, let's do f of negative 1. Now, we know that if you do f of negative 1, this is saying x is negative 1. Well, we have three pieces here. I'm going to call it piece 1, piece 2, and piece 3. So if x is negative 1, I first have to figure out, based on these domain pieces, which part would contain x less than x of negative 1. Well, it's going to be in piece 1 because piece 1 is where I plug in all x's that are less than 5. So piece 1, if I plug in negative 1, piece 1, I'm going to put in 2 times negative 1 plus 1, which is negative 1. So you just have to figure out which piece you're plugging in and then substitute it in. If I do the same function, I do f of 6. Well, 6 is valid for piece 3 because that's valid for x's that are greater than 5. So 6 squared minus 4 is 32. Now, the most interesting piece is typically the breaking point, like f of 5. Now, f of 5, we have to figure out where is x of 5. Well, x of 5 is valid on piece 2, and it just has the number 5. Basically, at x equal 5, it's 5. So that would be our values. So there's one function value from every piece. So you have to figure out where your x value, which piece of the function, you're going to plug it into. Now we can also graph piecewise function. This is how we get some of those weird graphs we saw in sections previous, where we're doing odd domains and ranges that were broken apart and stuff like that. To graph a piecewise function, we'll practice this quite a bit. We're just going to graph each piece in its domain. So we're going to look at all the different domains and we're going to graph each piece independently. Now I do this with some different tables and we'll kind of see how this works, and I'll show you just a very, very simple way how to graph these piecewise functions. So let's look at these two functions. So the first one I have is f of x equals x when x is less than 0. So again, valid when x's are less than 0. And x squared when x is greater than or equal to 0. Now we know this is kind of a line, and we know this is kind of a parabola of some sort because it is a square. So we have these two pieces. So I'm just going to call the line piece 1, and we'll call the parabola piece 2. So essentially this thing is going to look like a line, and then it's going to magically turn into a parabola. So if I look at some of the values, so if I look at f of 2, that means x is 2. So which part has x of 2? Well, 2 is greater than 0, so that is going to get plugged into piece 2. So f of 2 in piece 2 is simply 2 squared, because the function's x squared, which is 4. Now f of 0 says, okay, if I have f of 0, that means x is 0. So we have less than 0 on the first piece. We'll know it is 0. X greater than or equal to 0 on the second piece, so it's on the second piece again. So f of 0 would be 0 squared, or 0, because in the second piece. So that's fine. That's how we do the function values. We can also graph this. Now there's lots of ways to graph it. Some people say graph it and cut it. I don't do any of that. I just make little tables. So what I would do for piece 1 and piece 2 is I'll just pick some different x's. Now I am somewhat limited. Piece 2 says take x's that are greater than or equal to 0. So maybe 0, 1, 2, stuff like that. And the first piece says take x's that are less than 0. So how about -2, -1, and 0? Now obviously 0 is not less than 0. So what we will represent, whenever you have a point, when you're taking the end, but it's actually not included, we will make that an open circle. So for piece 1, we just plug all the x's in for x. Well, that's kind of boring. It just becomes the same. So -2, -2, -1, -1, and 0, 0 is an open circle. So if I graph this portion of the graph, I'm going to have an open circle at 0, 0. And then at -1, -1, I'm going to have a point. And then at -2, -2, I'll have a point. So then this graph will kind of go like this. So essentially it looks like a line that's basically cut off. So I'm only graphing the line for less than 0. But again, just pick some x's less than 0. Make sure you pick the boundary point. So you got to really do want to make sure you pick 0, because that's going to kind of tell you where the graph is getting close to. Now for piece 2, I'm going to plug these all into this guy, which says square them all. So 0 squared is 0, 1 squared is 1, and 2 squared is 4. So in this case, 0, 0. Now in this case, it's definitely a closed circle, because 0 can be equal to. But ironically, 0, 0, it's basically going to fill in that open circle. So these are going to connect. They don't have to connect, but in this case they do. So it looks like this. Now, I want to make sure that I know it's somewhat parabolic, because I know it's curved, it's x squared. So now it looks like this. So what you can kind of see here is we have this line, right? You have this nice line, and then we have it turning into this parabola. Obviously, the rest of the parabola would be over here, but we're only doing x is greater than equal to 0. And the rest of the line would look like this, but we're only doing the line for x less than 0. So there is our graph of our piecewise function. All right, so let's look at another one. This one's kind of odd. So in this case, we have two pieces again, but we have 1 over x. 1 over x we know is just a reciprocal function. An absolute value of x is obviously an absolute value of x, which is some kind of v. And we'll see what kind of parts we get, right? So If I look at some of these questions, so we have x greater than or equal to -1, we'll call this piece 1, and x less than -1, we'll call that piece 2. So if I'm doing f of -1, that means x equals -1. So x is equal to -1 in piece 1. So I'll do 1 divided by -1, which is just -1. The other function value I'm looking for is f of 3. So f of 3 is going to be, obviously, 3 is definitely greater than or equal to -1, so that's also going to be in piece 1. So f of 3 is also in piece 1 because 3 is bigger than -1. So it'd just be 1/3. If I wanted one for piece 2, I could do like f of -2. F of -2, because -2 is less than -1, so that would just be the absolute value of -2, which is 2. So that's fine, but let's go ahead and graph this. So we know absolute value is kind of half of v, and we kind of know a reciprocal function has that asymptote and all that. But we might not see all of it, because remember, we're doing a piecewise function, we're only looking for portions of it. So I'll do piece 1 here, and I want x's that are greater than or equal to -1, so I'll go -1, 0, 1, stuff like that. Maybe 2 as well, because it's kind of a weird function. Piece 2, I'll go ahead and I'll pick x's that are less than -1, -1, -2, -3. Now again, I did pick -1, so that's going to be an open circle. And it's going to be a closed circle at -1 on piece 1, because on piece 1 it has the equality. So now I'm just going to plug these all into piece 1. So piece 1 says take 1 over that value, so 1 over -1 is -1. 1 over 0 is undefined. That's kind of weird, but if you remember, at 0 on the reciprocal function, we had a vertical asymptote, if you remember that from our initial types of functions. And then we have 1 over 1, which is 1, and 1 over 2, which is 1/2. So let's just go ahead and graph that piece first. So -1, -1 is a closed circle, so it looks something like that. At 0, there's an asymptote, so it's going to look, we just kind of put a dashed line sometimes to signify that. 1, 1. 1, 1 is going to look like this, and 2, 1/2 is going to look like this. So if you recall from the initial stuff we did, it kind of looks like this. So if I kind of follow that, I know this piece is going to look like this. And this guy should just dive down here, because I don't want the parts to the left of it. So basically, I'm cutting it off here and just doing the stuff to the right. Now, piece 2 says take the absolute value. So the absolute value of -1 is, of course, 1. Absolute value of -2 is 2. And the absolute value of -3 is 3. So if I plot these points, and now -1, 1 is an open circle. -2, 2 is a dot, and then -3, 3. So this one looks like this. Now, you might say to yourself, that doesn't look like a V, and I agree. But remember, absolute value would kind of look like this, so the V would occur at 0. We just don't get far enough into it. So when you look at it, it kind of looks just like this line part, because we're not seeing the rest of the absolute value. So again, if it's not equal to, we just use an open circle. If it is equal to, we use a closed. We just kind of graph each part, and that's going to make our piecewise graph. Some will connect like the first one, and some like this one will not connect. Just depends on which functions you have. Let's look at one more. This one has 3 pieces. This one has x minus 2 for x less than 0. Well, that's just going to be a line. We'll call that piece 1. 5 when x equals 0. That's going to be just a number. And 3x minus 2 when x is greater than 0. We'll call that piece 3. Okay. Now this one's talking about domain and range. That's typically easier done once you have the graph created, so we'll look at that later. Now if I do f of 0, ironically f of 0 means obviously x is 0. So the only one that has an x of 0 is that middle piece. So that's in piece 2. Now piece 2 says if x equals 0, then it's just 5. It's just a number, so we just say it's 5, so it'll be 5. Okay. So The rest, let's go ahead and graph it before we try this. So I'm going to try to graph these three pieces using little tables, right? I'll even do a table for piece 2, although it's going to be pretty boring. So piece 1, x and y, piece 2, x and y, piece 3, x and y. So let's do piece 1. Piece 1 says take x's that are smaller than 0. So I'm going to go 0, -1, and -2 because those are smaller than 0, except obviously 0. So that's going to be an open circle because I know that it's not including 0. Now piece 2, it only includes 0, right? So I'll only put 0. And it is closed because it is equal. It's the only point literally there. And piece 3 is x is greater than 0. So let's go 0, 1, 2, 3, whatever. But this one's going to be open. Okay? So if I plug the ones for piece 1, it says x minus 2. So I'll take the x's and subtract 2. 0 minus 2 is -2. -1 minus 2 is -3. -2 minus 2 is -4. So we have, so if I want to plot that point, 0, -2 is open. -1, -3 is going to be here. And then -2, -4 is going to be here. And we know x minus 2 is just a line, so going this direction, we're just going to have some kind of line. Now in piece 2, it says the x is 0. Well, it literally says here, if x is 0, then it just says 5, so it's 0, 5. So whenever it has just a point there, it's just going to be a dot. So at 0, 5, that's my point. There's nothing else. Okay? Then for piece 3, we want x's that are greater than 0. It's 3 minus 2x. So 3 minus 2 times 0 is 3. Open circle. 3 minus 2 times 1 is 3 minus 2, which is 1. 3 minus 2 times 2 is 3 minus 4, which is -1. And 3 minus 2 times 3 is 3 minus 6, which is -3. So those are my points that are going to be on piece 3. So I'll have 0, 3, which looks like this. 1, 1, which looks like this. 2, -1, which looks like this, and 3, -3, which looks like this. And it's going to go something like this. Okay? So now that you see this, we can certainly do domain and range for this graph. Now if we look at the domain is kind of odd. It's going to start at -infinity, no problem. The first point we really have to check is 0. So open circle, but there is a closed circle, right? So as long as there's a closed circle, it's included. And then there's x's going this way, so it actually goes forever. So our domain is actually -infinity to infinity. There's no gaps in it in this problem. Now range is a little more bizarre. So the lowest range is obviously -infinity because we actually have 2 lines pointing down. So we kind of keep going up, up, up. Now we have a gap. So we have an open circle at 3. So that's going to be the end of our range temporarily. Now it's kind of odd. There's nothing really above it except for one point. There's literally a point at 5. So you could do it a couple ways. Some people would just say 5 to 5. This is one way to do a number. Some people would just say -infinity to 3 union the single element of 5. I don't really care. Both would be fine. So no gap in the domain, but certainly a gap in the range. So the last kind of thing we're going to do is we're going to use a graph to find some functional values using a piecewise function. So again, just remember when you're talking about using a graph that, you know, if you have f of something, that's the x value, and if you have it equal to a number, that's the y value. So here is a piecewise function. Now kind of interesting here, we have a closed dot here, a closed dot here. Now interestingly at -1, open circle here, but closed dot here. Okay? So if I do f of -1, this is basically saying what is the y value when x equals -1? Well, here's -1 where they've lots of circles, but that's open, that's closed. So the only closed circle, the only y value at -1 is 1. The rest are kind of straightforward. You have f of -4, x is -4. So there's -4, I go up there and I am at 7 it looks like, so a y of 7 for an x of 4. f of 2, that means x of 2. So if I go to x of 2, here's 2. The y value appears to be 6. And then finally, f of 6 means x equals 6. So if I go to 6, well, I don't see any graph over here, right? There's no graph, so that seems to be out of the domain. So the way we say that is we just say does not exist. There is no point on this graph where it has a y value with an x of 6. Now, if it went something like this, sure, we could probably find it, but in this case, it doesn't. Finally, the last one, so we have some, these are written a little different. It says f of x equal different values. So this first one says f of x equals 0. This is basically saying if y is 0, what is x? So 2 points that have a y of 0. And they're not perfect, but we'll approximate. X is about negative 2.2-ish, and the other one looks like 1-ish. That one looks okay. The second problem says, all right, f of x equals 6. Where is y equals 6? So if I go to my graph and I look, well, this definitely has a y of 6, and this definitely has a y of 6. So I look like 2 spots. So one looks to be 3 for sure, so x equals 3. The other one, I don't know, negative 4-ish, maybe negative 3.75. Again, not going to be perfect, but approximate. And this one appears to be the same problem. So just for fun, let's go ahead and change this one to negative 6. When is f of x equal to negative 6? Because it's an interesting question. I think that's what I meant to put. So if you go to negative 6, this is the only point that has a y of negative 6, but it's an open circle. So we can't have open circles, so we just say does not exist. So that just means no points have a y equal to negative 6. So piecewise functions, as long as you take them slow, do them in parts, nothing really to them. We'll obviously work more on these next week and practice them as well.